last lecture, we constructed an explicit field of complex numbers, a field which contains R as a subfield and a root I to the polynomial x square plus 1. We also showed that if there is a subfield of the field of complex numbers which contains R and I, it should necessarily be the entire set C. We also showed uniqueness up to field isomorphisms of the field of complex numbers. So hence we can talk about the field of complex numbers here. So let's start this lecture by pinning down one of the observations which we made during the construction of the field of complex numbers. So in the last lecture, we proved that C is a two-dimensional vector space over R. C is a two-dimensional vector space. We in fact got hold of an explicit basis. So what was the basis? 1 comma I, where I is the coset representative of x. 1 comma I turned out to be the basis of C over R, to be a basis of C over R. So let's do one thing. Let's define, or let's gather all the elements of the type. Let's see the set of all A plus Bi, where A and B are real numbers, and 1 and I will form a basis. That is going to imply that A plus Bi is, so let me start with, since 1 comma I is a basis, A plus Bi is equal to C plus Di if and only if A is equal to C and B is equal to D. We even have an explicit expression for the addition and multiplication. So addition, what was the addition? A plus Bi plus C plus Di is equal to A plus C plus B plus D times I. And how about multiplication? We also define the multiplication as being the product of cosets. So it will manifest in this manner here: A plus Bi plus times C plus Di. This is AC minus BD plus AD plus BC times I. So if you have not seen a course on abstract algebra or ring theory, you may as well start this course, complex analysis, here by taking this as our definition of field of complex numbers. It's a collection of all elements of the type A plus Bi, where A and B are real numbers, and addition and multiplication is defined in the manner written here. And you can sit down and check that C is a field of complex numbers with these definitions, with these operations. Alright, so any two-dimensional vector space from your course on linear algebra, you will be aware that this is going to be isomorphic as vector spaces to R2. So by looking at the linear transformation which sends 1 to 1 comma 0 and I to 0 comma 1, we could also define a field structure on R2 using this definition, using the linear transformation from C to R2, sending 1 to 1 0 and I to 0 comma 1. We can identify C with R2. And what will be the multiplication? Remember that R2 is just a vector space. There is no multiplication of two vectors in R2. There is a scalar multiplication which comes from the vector space structure. However, we don't know how to multiply two vectors here. Now we can define multiplication on R2. So for AB and CD in R2, define AB times CD to be equal to AC minus BD, comma AD plus BC. So this is the definition which I would like to give now, which is nothing out of the blue. I'm just using this particular definition to say that what the multiplication in R2 would be, and this particular definition is something which we had obtained from considering the coset representative or the coset multiplication of cosets in R of x mod x square plus 1. So we are using our prior knowledge of whatever we had done in the last lecture to talk about the multiplication here. And again, it's a slightly tedious check to see that with this multiplication and the usual coordinate wise addition, R2 turns out to be a field of complex numbers. So whenever I am saying it turns out to be a field of complex numbers, there are a few things to be checked. One is that it's containing R as a subfield. The second is that it contains I, which is a root of the polynomial x square plus 1. And finally, that it is the smallest such fields. If you have a subfield of C or R2 in this case, which contains both R and I, it should necessarily be equal to R2. So these things have to be checked, which we have already done by using the algebraic machinery in the previous lecture. If you have not followed the previous lecture, let me stress upon the fact that you can take this as the definition of the field of complex numbers, and we will be using this notation in this particular course. Our complex numbers will always be written as A plus BI. So let me do one thing. Let me set a few notations straight for this course. So in this course, if Z is a complex number, then Z is equal to A plus BI for A comma B in R. This is the expression for the complex numbers that we will be using. Okay, what is A and B? A is the real part of the complex number Z. So for Z, a complex number, Z is equal to A plus IB. A is called, so this A is not the article A, it is this A. So A is called the real part of Z. And is denoted RE of Z. And at the same time, B is called the imaginary part of Z. And is denoted IM of Z. If A is equal to 0, then Z is called purely imaginary. There is no real part to it, it's called purely imaginary. And if B is 0, it's a real. And if B is equal to 0, then Z is purely real or is a real number. Oh yes, I should have mentioned it here itself. The vector space R2 is something which you might be very familiar with. It's the plane which we are usually accustomed to, and we are familiar with the geometry there. And because C can be identified with R2, the field of complex numbers is also sometimes referred to as the complex plane. So let me just note that here, since C can be identified with R2, the complex field, the field of complex numbers, is also called as the complex plane, is also referred to as the complex plane. Okay, now that we have invoked the identification, let's see what happens. So this can be thought of as the complex plane. We have the x-axis and the y-axis. The identification which I wrote earlier was by sending 1 to 1, 0, and therefore the x-axis consists of real numbers. The real numbers, and it's called the real axis, purely real numbers, and hence called the real axis. So when we say real axis, we mean the x-axis. And what if A is 0, then A is, if in A plus IB, if A is 0, then BI will be mapped to 0, B, and that will be the y-axis, right? The y-axis consists of purely imaginary numbers. And is called the imaginary axis. Okay, now that we have done away with the obvious things, okay, more notations are in order. For n non-negative integer, okay, before we talk about non-negative integers, by convention, you raise a complex number to the power 0. Maybe I should say this after, it's okay. By convention, z to the power 0 is defined to be the unit element 1. For n non-negative integer, we will define z to the power n inductively. In fact, z to the power n plus 1 inductively is defined as z to the power n times z, assuming that z to the power n has already been defined. Oh yes, by convention 0 to the power 0, this is also defined to be 1. And for a non-negative integer n, z to the power n plus 1 is defined as z to the power n times z. That's for non-negative integers. What if n is negative? So for n less than 0, let n be equal to minus m. Then z to the power n is defined to be 1 by z to the power m for z not equal to 0. We can't talk about inverting 0, right? So for z not equal to 0, z to the power n is defined as 1 by z to the power m, where m is minus of n. Okay, so these are the usual notations which we have borrowed from field theory. That's how we define the exponentiation. In this course, we will be defining exponents with arbitrary exponents, but we will come to that later. Okay. Let's next introduce the important concept of conjugation. Let's take a complex number z, which is say a plus bi in C. We define the conjugate of z to be the complex number z bar. It's denoted as z bar and it is defined to be a minus I times b. It's an immediate check for you, which I will leave as an exercise to see that if you look at z plus w bar, this is z bar plus w bar. And if you look at z times w bar, this is equal to z bar times w bar. You could write it down explicitly in terms of coordinates, compute both left hand side and right hand side and see that they do match. Let's look at some of conjugation. So if z in C satisfies z is equal to z bar, suppose a complex number is equal to its conjugate. If you write it down in coordinates, let's see what happens. Then, so let z equal to a plus ib. Let me write it that way so that I already have the coordinates. A plus bi in C satisfy z is equal to z bar. That means a plus bi is equal to z bar, which is a minus bi, which implies that 2bi is equal to 0, which implies that b is equal to 0 since 1 and I are forming a basis. So b is equal to 0 tells us that z is a real, right? That means z is real. If z is real, then naturally b is equal to 0, right? And therefore z is going to be equal to z bar. So hence we have a small observation here which I will write as a lemma. A complex number z satisfies z is equal to z bar if and only if z is in R. So let me slowly start doing this identification of R with the real axis. I'll write z is in R. Basically, this means that the imaginary part is 0. We could actually use the conjugate of a complex number along with the complex number to compute both the real and imaginary part. So notice that if you look at z plus z bar, observe that z plus z bar is just going to be equal to a plus bi plus a minus bi, which is equal to 2 times a. And therefore, you can say that real part of z is equal to z plus z bar by 2. We could do a similar computation and get hold of an expression for the imaginary part of z as well. You should check that this is z minus z bar by 2 times I. Remember that it's a field, you can invert I as well. So this is what imaginary part of z will turn out to be. The conjugation is a notion which you will be actually familiar with from linear algebra. Geometrically, this is something which you would have already seen. So if geometrically, let's see what happens. Geometrically, if I have to draw the complex plane this way, and suppose this is our point z is equal to say a plus ib, a plus bi, or if you prefer the R2 form to look at it, this is the tuple a comma b, and it's being sent to a comma minus b. So that will be some point here. This is what our z bar is going to be, a minus bi. It's basically the linear transformation which reflects every vector along the real axis. So geometrically, conjugation is the linear transformation which is the reflection along the real axis. Okay, this is our R, this is our Z, and this is what our Z bar will turn out to be. Okay, so now let's take the first step towards studying analysis. And to do that, let's try to see the topology on the field of complex numbers. But before we explore all that, let's define a function. This is actually being defined in order to get to the stage where we discuss the topology on the field of complex numbers. So let's define a function for z in C. Let's take any complex number, n of z be defined to be z times z bar. So it takes a complex number z, it gives you another complex number z times z bar. So this is the function from C to C. But there are a few observations immediately which we can make. What is n of z bar? Notice, we should write it down carefully. Notice that n of z bar, this is just going to be equal to z times z bar the whole bar, and this is going to be equal to z bar times z bar bar. This point, maybe I should go back and show you the definition of field of complex, the conjugation on the field of complex numbers. So from here, an immediate observation would be that conjugation, the process of conjugating is an involution. So for z in C, notice that z bar bar is just the conjugate of a minus bi, which is a plus bi, which is equal to z. So if you take the conjugate of a complex number, you get back the complex number z itself. And with that observation, let's see what happens to our n of z bar, and this will just turn out to be equal to z bar times z, which is the same as z bar, and hence this is equal to n of z. Then we just observed a few minutes back that a complex number is equal to its conjugate if and only if it's a real number. This implies that n of z belongs to R, and therefore n is a map from C into R. We already saw that n of z bar is n of z, so is n of z bar. Also, this is something which I will leave it for you to check. N of z bar is the same as n of z. The same argument. What next? Okay, an important property of n is that n of z times w is equal to n of z times n of w. So this function is many times referred to as the field norm, and it is an algebraic concept. It's actually a field norm of C over R. Why did we discuss n? We will come to that in a moment. So just remember that this is an algebraic concept, and in order to talk about the topology, we need to talk about, well, we don't need to talk about, but here we will be talking about a metric on the field of complex numbers, and our next goal would be to explicitly get hold of the metric with which we will be working on the field of complex numbers. The field of complex numbers, from your course on linear algebra, you would be familiar with it. This is an inner product space over R. So let me not write field of complex numbers, because it is of course a field of complex numbers, but now we are looking at it as a vector space. We know that C has an inner product, a real inner product. Maybe I should write it down very carefully. Inner product over the field of reals defined by inner product of z comma w. This is defined to be the real part of z w bar. This is the inner product, the standard inner product actually, which we generally consider over, which we generally consider on C when considered over the field of real numbers. This is an inner product. With this inner product, C is an inner product space. I will not go into the details of checking all that again. C is an inner product space. You should brush up your linear algebra, or you can just sit explicitly and check that this is an inner product on C, a real inner product, which makes C into a real inner product space. Maybe I should mention that C is a real inner product space. What will be the norm that we get from this particular inner product? This inner product can be used to define a norm. The norm of a function, norm of an element z, this will just be the inner product of z with itself to the power 1 by 2, which is basically real part of z bar to the power 1 by 2, which is equal to the real part of n of z. You see, the n of z has featured in now. But n of z is always a real number. And what do we know about real part of a real number? It will be the real number itself. So this is just n of z to the power 1 by 2. The effort put in to define n of z, which is a field norm, which is an algebraic concept, is to tell you that the norm with which we will be defining the metric is defined using the field norm, which is invariant under isomorphism. So for an isomorphic copy of C, we can talk about a corresponding n, and we can talk about the norm obtained in a similar manner. Therefore, whatever the metric we define using this particular norm, it does not depend on the explicit construction of the field of complex numbers. And that's precisely the point that was being driven home. Okay, so let's see what happens in coordinates. If z is equal to, say, a plus bi, let's see what n of z is first. N of z is basically a plus bi times a minus bi, which you should check is just a square plus b square. And therefore, the norm of z, this will be a square plus b square to the power 1 by 2. Let's see what happens when z is a real number, just a real number. If z is real, then b is equal to 0. And this would imply that the norm of z is equal to a square plus 0 to the power 1 by 2, which is just the absolute value of a. So the left hand side, when I say, which is, so this is basically the left hand side is the norm and the right hand side is the absolute value. Therefore, the norm which we just defined, naturally extends the absolute value which we are familiar with on the field of real numbers, extends the absolute value on R, and therefore the norm on C will also be called as the absolute value, and hence the norm on C will also be called the absolute value. All right, so in any normed vector space, we can talk about a metric. Let's now define a metric on this particular normed vector space. In other words, let's define a metric on C using the norm which we just defined, the absolute value which we just defined. It's going to be the, we'll just use the standard definition using this absolute value. Let's start using the word absolute value. We define a metric D, which is from say C cross C into R given by D of ZW. Let's take two complex numbers Z and W. This is defined as the absolute value of Z minus W. This will turn out to be a metric on D. I'll leave it as an exercise for you to check that this indeed coincides with the metric on R2, which we get using the standard inner product on R2. That's the metric with which we have studied all the real analysis on R2. And therefore, the topology that we will be looking at on C coincides with the usual topology on R2 which we are familiar with. So let me just note that down. So this metric coincides with the usual, it's called the standard metric, usual standard metric on R2. What was the standard metric? D of x1, y1, x2, y2 is the square root of x1 minus x2 the whole square plus y1 minus y2 the whole square. You should check that this is exactly the metric that the D which we just defined will give us. So this is going to coincide with the standard metric on R2, and hence the basic topological notions of open sets, closed sets, boundary, convergence, limits, continuity, all these things are the usual notions, topological notions we are familiar with from a course on real analysis, and hence the topological notions on C coincide with R2. So a very key observation at this point is that the metric that is being defined, I already made this, but let me stress home the point, this observation. The metric D is defined using the absolute value, which in turn is being defined using the field norm, which is an algebraic property. So if you go to different construction of the field of complex numbers, there will be a corresponding field norm there, and we can do all these things again. So basically the analysis that we will be doing, the topology and the analysis that follows, is going to be invariant under which choice of complex numbers you pick. In the next lecture, we will recall some of the cardinal aspects or cardinal topological notions that will be needed in this course. Let me stop this lecture here.